gone 7 o'clock in the evening, CAT. So I'd like to say a very big welcome to all on channel this evening to the BACAR-13 Journey to the Edge of Space talk. We have a number of guests that will VIP guests that will be presenting tonight. So there will be some switching between presentation material, but we would like to entertain you and show you all about the BACAR-13 flight that took place on the 11th of October to the edge of space. I am sitting here in a room with a few other radio amateurs, and we're watching this on the big screen, and we will start with the presentation now. So the agenda for tonight, we'll go through the BACAR-13 stratospheric balloon missions, and I think that will be done by Christo. Then we'll talk a little bit about mission planning and launch details, also from Christo. Then overview of the payloads on BACAR-13. And we're going to go through each, or not all of them, but we'll go through several of the payloads that were flown on BACAR-13. And into their payload, what they discovered, what they learned, what worked, what didn't work, and the results of their flight. Then we also have a pressure pop, and we will see the return and recovery of that. So there's a number of presenters, as mentioned. We'll be switching various presentations this evening. So there on the far right-hand side, you can see an image of the BACAR balloon with all the payloads, and you're going to see that several times this evening. And on the left-hand side, you can see one of the images that was transmitted on the UHF SSTV transmitter. At this point, I'd like to hand over to Christo, ZR6L through BACAR-13. So lead in on Christo. Christo has been the to date as part of the Secunda Amateur Radio Club, with all the members of the Secunda Amateur Radio Club and the Hamnet team that have always consistently supported BACAR and been the team that recover the payloads. Christo, can I hand over to you? Are you going to present?
Okay. This slide here, thank you, Keith, and thank you for inviting us. And I want to congratulate you on this this initiative that you have, Power Hour. I think for us as radio amateurs, this is very nice, and it's a very good platform to share information and experiences. Yeah, this is for me a very nice slide that you got there. Keith, can you advance the slides, and then I'll talk through them. On this computer, I don't have that other slides that I sent you previously. Okay, but if you go one back, I just want to say something about that previous slide. On the previous slide, yes, that one. Yeah, as you can see there on the right-hand side, there's the cheap yellow displays. I bought two of them in error, but eventually I decided I must use them and see what I can do. And then I decided I must use some of ChatGPT's skills to help me and develop two screens. The one at the bottom shows a weather station that I had on the site with the wind speeds and the gusts and some temperature for the day, as well as the SSID it's connected to and the Wi-Fi that is connected. Not have the BME 280, therefore there was no humidity. But this was very nice to develop and see that at the base station to see what is happening to the balloon. On the top one, you can see the position or the where the balloon was, at what altitude it was. Unfortunately, I see the kilometers and the heading did not display correctly there in the table. But if you look at the compass there, the cardinal compass there, you will see that it did display where it was, and at the south there, you can see how high it was at that stage. Luckily, this year we did not have high winds that would blow the balloon a lot far away. But guys, if I can urge you to buy this cheap yellow displays, is about 280 Rand. Um, on the right-hand side, you can see there that black part on the right-hand side, that's the Wi-Fi antenna. This board is great. You can do a lot of things with them. Okay, that's the this slide. The next one, Keith. Introductory slide. A very nice picture of our town and my place of work in the back left-hand side there. And why? Yeah. The next one. All right. Why do we do BACAR? Why do we do this thing? I was thinking about that today, and I thought we are radio amateurs by nature. We explore. It's just the way that you are wired. That's why you are a radio amateur. We like to explore. On BACAR specifically, I wanted to keep the history alive. Hans started this thing with a team of people. Some of them is still alive today. I think Hans is the eldest still living. That started this in the 70s. I can distinctly remember on YouTube there's a video of them. Please go and search on YouTube for BACAR. There is about an hour and a half video of Hans and his teammates doing BACAR. It is absolutely interesting to imagine that the guys, what they did that day. It's so interesting. But I wanted to keep the history alive. And we love fun. In Sekunda Radio Club, we love fun. My friends, we love fun. And as radio amateurs, we must have fun. Everybody thinks that we are old people sitting there behind a radio and try to make it talk to somebody else. It's not like that. We like to have fun and enjoy what we are doing. We tinker. Um, we figure out stuff and we try that and we keep on trying until we find the results that we want. So we like to tinker, and I think we are good examples for the youth to follow in our footsteps. If there is one thing that the youth must try to realize is that we have no boundaries. There is, but we don't look at that so much. We try whatever we want to do and then try it and then see what happens. And I wish they can learn that because it seems like they were only born in boxes. But we like to inspire them. And if we can do what we are doing now, they would be able to do at least 20 times more that we do because of the technology that on the next slide, please, Keith. And of course, for me personally, this is what I do BACAR for, is for this type of picture. Where can you take a picture of the darkness of space? Only on the BACAR. And I think this is for me the one slide that I will always remember about the BACAR initiative is I want to take the picture of space. And I'm not getting into one of Elon Musk's rockets to go and see space because I can see it from here. And we have our own initiative. The next slide. There's just a picture of our payloads, and this is a picture of about 2 years ago. And I must say that this year the payloads was much more professional and much more neat in the way it was in the way it was done. That parachute there has flown quite a few times. In the last 2 times it did not deploy so nice, but we do have videos of it deploying, and it is on YouTube. The next slide. All right, what is a BACAR payload? I think we must just talk a little bit of what is a BACAR payload. In the specifications, I think this is what we promote most, is let's stay below 500 grams. Let's do it in a 1 liter cube. And if you add the protection and the isolation, insulation, it's about 14 by 14. The systems that usually should be on board is the power supply, a microcomputer of some sorts. There's quite a different. You can use anything that you want. Sensors, cameras is sensors, and thank you, Keith, for your sensors that you have put up. Experiments, I'll show you another picture later. And then RF packages. Some of the payloads have RF packages. We are amateurs, radio amateurs. We need to have some RF packages. The next slide. Something that I would just like to share, and I have not seen this on any other balloon missions on YouTube yet. And this is something that we have, I think we have developed in our BACAR program. And that is to have the four lines through your payload. The payload swivels up and down on the strings. I think this method of connecting all the payloads in the train is something that we have developed. I've seen one or two videos on people in the US with youth camps and that is also now doing it this way. In terms of redundancy, you will not lose a payload this way. I think this is something to note that we have developed as part of the BACAR program. On the next slide. Yes, what have we achieved? Oh, scheiße. On this middle one, Keith, I'll fix and send the right one to you so that you can include it in the final PDF. But this is the heights the altitudes that we have achieved. If you can look there in 2017, we went to 31 kilometers, and 22, we went to 13 kilometers. And then if you look at 22, the amount of teams and the amount of payloads is a bit different. Therefore, I think at those dates, the whole train was a little bit lighter and we could go a little bit higher. And just look at the altitudes, it's more or less 30 Ks that we went up every time since 22, because I think that we got a little bit more focused. And our predictions and our filling systems and the way we do it just got a little bit better. I don't know why the teams doesn't show, but this year, the past year in 2025, we had 11 teams participating. So yes, I don't know. This is bad for me, but yeah, I'll fix this up and send it to you, Keith. On the next slide.
No problem. Thanks. We'll get the updated.
Yeah. So how do you arrange this thing? How do you arrange a BACAR launch? And I try to be as concise as possible. And the one thing that is very important is fix a date. You must have a date when you are going to launch this thing. Otherwise, none of your planning is going to work out. You have to have this date. So we have fixed it for BACAR. It's always going to be the second week in October. It's the end of the school holidays. The winds is favorable. Because the next point there, check the weather patterns. We are situated in Secunda. The winds predominantly in South Africa goes from west to east. Therefore, if you launch on the western side, it creates problems with ATC. Therefore, we launch on the eastern side of Oliver Tambo. And then you have to get people to participate. That is probably the most important thing, except for fixing the date and then checking the weather patterns, is get people to participate. And this year, I want to just highlight Hendrik. He's here tonight with a presentation on Cameron. He's the son of Guy that is also here today. Cameron is building a particularly very interesting payload that we would probably launch next year. As you all know, time just runs out so quickly. And yeah, and he had a lot of other things to all. He also got married this year, last year. And so his time ran out very quickly. Hendrik, I found him at the, which was it, in May? I found him there at the SIRL conference, and we chatted a little bit. And then after that, I sent him a lot of stuff on Pudo, and Hendrik built quite a few things for us that we are going to see, and we are looking forward to his payload for next year. We got a lot of lessons learned, but you will see that later tonight. And then we also need to fix the launch site. And there is fixed routes of commercial aircraft in South Africa, so we will try to stay out of it. And fortunately, Sakuna is situated in a sector that doesn't carry a lot of traffic through the day. You can imagine all the people coming from the Cape. There's almost a plane every half an hour coming from Cape Town. There's a lot of guys coming in from Namibia, Botswana on the western side. Here by us on the eastern side, there's not a lot of places, that's poor guys from Australia that wants to come home a little bit, and then some guys from Singapore. Most of the India traffic, Afghanistan, and all those places, they come from the north corridor. Therefore, we have a nice launch site in Secunda. And then you need to apply for the flexible use of airspace. Yes, this is a very interesting thing to do, but not difficult. We gave them the area that we are going to fly in. There is 4 geographical points that we give through to the ATNS and CAA. In this area, we are going to operate for a fixed time. We give them that information as well. Then they decide. They always come back with answers. It doesn't matter what you tell them. And through the years, we have a very complete application now, showing them everything and what we are going to do and tracking systems and all this, but they still have answers. I think to this year is the first year that they didn't ask any question, because I think we have answered everything up to now. And on this point, I need to give Tom van der Bon, I think that is ZR6TG, some recommendation. He bought a DSB beacon for us that we can put in the payload. So every aircraft equipment on their dashboard will be able to see the balloon. They would only be able to do that for about 15 minutes, because then we are out of controlled airspace in any case. One other thing is, and I'm glad Keith is here, because Keith helped me a lot with updating everybody with everything all the time. It does take a lot of time to update everybody with what is going on, where are we in the process, and what we are doing. Constantly for the last month, we check weather and flight predictions. Like the year before this, we had to postpone because of the weather conditions. And then you have to communicate the launch day arrangements, makes all the correct, every people involved. Gert needs to contact the emergency services. Gert contacted Hamnet, and all of those things that needs to happen. Everybody wants to stay somewhere. All of that needs to be done. Then we launch and recover the payloads. We review the data. This is very nice. Everybody enjoys this part. And then we plan next year. You can go to the next slide, Keith. Did everybody hear me? Because my connection is a bit unstable. So I think at this point I want to just give thank you to the SIRL and the committee for supporting this initiative. Without them, it would be very difficult for us to do that, and there would have been much more entrepreneurial to make it work. Then our local club, the Secunda Radio Club. I think with their support, it would also not be very possible, and we have a very good buy-in there. The support for Hamlet for the recovery of the balloons. Last year they had a very interesting recovery. I spared them this year. And then, of course, the amateur community, everybody that participates. It is so nice to see the people who participate. There's people from Botswana that participated. He almost decoded all of the UHF SSTV. It was so nice to see that. And how far is he from Secunda and from our launch site? So I think everybody in this meeting as well. This is so nice to experience this and the support that we get. On the next slide. Yes. Okay.
Thank you very much.
I think the next slide just shows us who was the participants. Thank you, Keith. Thank you for the time, guys, and thank you for listening to me. I will mute now, otherwise the Scottish Terriers will irritate you.
Thank you very much, Christo. And I think you understate your role in this significantly. You set up the WhatsApp groups and you do all the coordination and the project planning, and you kick our butts. Sometimes when we get to my presentation, I'll give you some of the butt kicking that happened to make me do a payload. But yes, so there's a list of the payloads. They didn't all fly. Unfortunately, I think Tom had an issue getting to the site. He had a work commitment that he couldn't get out of, a crisis at the end of the day. And I think that there was one particular Sansa, the Project Magnisphere. I don't think they managed to get to site. Christo, I know that you had arranged with them, and I think they from the Natal University, if I recall, Christo.
Actually, they are from Sansa itself, from Hermanus, but they work together with people in Poland to develop the payload. And then their timelines just didn't work out. I think we must just keep the relationship warm so that we can get them here and to let them do that test. The work they are doing is absolutely interesting. I don't know if any one of you ever went to Hermanus and to the Sansa there in Hermanus. It is so interesting the stuff they do there in terms of magnetism, everything. It's very interesting.
Thank you, Christo. And then there was, as you indicated, one that didn't quite fly, but it's going to be there next year. So we'll keep that as a secret for next year. Right, at this point in time, there's a couple of the images of Christo's developments. You didn't speak about your specific payloads, Christo, other than obviously the displays that you showed right in the beginning. Do you want to talk to these?
Yes, Keith, I can go through this one. This is just a LoRa tracker that I've built. It's a very nice. I use some software from a guy in Chile, I think he's from, but it works absolutely great. This tracking software that I have here, loaded on this thing, also ground station, and Gert used the ground station, and it was actually very nice to see Gert using it, because the ground station interpret it as and it gives him the heading, the distance it is, and the elevation. So it is very nice software. This payload also transmitted 4 different modes. It transmitted normal APRS 1200 baud on UHF. It transmitted in LoRa at I think it's mode 0. Because Willie and I, Z6 VBT, developed a ground station that we use, so we can get that information from it. What you see on that first slide that Keith showed, that cheap yellow displays, that is where it come from. It also transmitted LoRa APRS, which is a very, very nice mode to use. It gets. I'm sitting in my house about 3 kilometers from the eye gate with a small rubber duck antenna that you get with the modules, and then it gets decoded by the gateway, or I gate more than 3.5 kilometers away. It's a very robust mode. And then last mode was RTTY, but difficult to decode because it's software modulated. Didn't work so well. I think next year I will just cut out the RTTY, leave the other three. But it was very nice building this, printing it. The battery was, if you can see there on the picture, the battery, I removed it from an old tablet, and then I put it in a holder that I laser cut, so that if it falls and breaks, that the LiPo doesn't burn out everything. But that is what I wanted to say about this one, Keith.
Thank you very much, Christo. Okay, let's move on then. So now I would like to hand over to Guy, ZS6GUY, and I know that he works with the Juchland Amateur Radio Club, and you can see the image on the screen. Guy, do you want to take us through this, and then you can share your presentation?
Sure, no problem, Keith. Let me just get the share part here. All right, you got my screen sharing there, Keith?
Let me just stop sharing my side, Christo. Sorry, Guy, please go ahead and share. I'm not seeing it yet.
Okay, let me do that again. Share.
Yes, you're sharing. Thank you.
Okay, great stuff. Thank you, everyone. Yeah, and a huge thank you to Christo and his team. It's been such a fabulous experience over the years. Just a little bit of the history that we have there. This is my 9th BACAR. We started in 2017. I think it was BACAR-5. And what a journey it's been. We've done various different things. Right in BACAR-5, we didn't know what to do and how to do it. And Willie graciously helped us along, and we put a light dependent resistor and a barometric pressure up to about 30 Ks. And that was a hell of exciting. And then we started getting creative, and we started adding accelerometers over the years and air quality sensors and GPSs, tried our hand at LoRa, put PI cams in and started broadcasting SSTV. And yeah, really the sky is the limit, as Christo said. It all depends on your imagination and what you want to do. Going through some of the stuff we did, we decided we needed to have a strong frame. And a lot of guys we saw were doing frames, 3D printed frames, wooden frames, no frames. And we came up with this design where we printed the smallest amount of plastic that we could, and we connected the tubes with carbon fiber rods that were hollow. And this gave us a very light frame that we were able to secure in the train, with the strings running through the printed blocks and actually through the middle of the carbon fiber tubes. And then we decided our experiment boards we're going to put, you'll see on the picture of the PCB, we drilled holes in it and threaded it through the carbon fiber rods. And this gave us a very nice stable platform. In the first couple of years, we actually filled the interior with polystyrene balls to try and soften any impact that might have occurred. And we were quite successful. The only problem with that was opening up the packages. There was just like polystyrene everywhere. So we decided to scrub that idea and put rubber blocks or rubber bands between the boards just to create a bit of a shock absorber. And then we started playing with PC boards. So when we first started with the PC boards, we were building our own. You'll see Willie's design on the top picture there. And we were printing them using the yellow type magazine paper and ferric chloride. And the problems that we experienced there was very poor adhesion of the yellow paper or the carbon on the yellow paper to the PC board itself. We picked up a problem with micro breaks on the PC boards caused by low DPI printing onto this board. And this effectively acted as a fuse every now and again and blew up the tracks. And I think this was compounded by the fact that the ferric chloride was taking too long to actually etch the boards. And a certain amount of undercutting of the track actually occurred as well. This we all figured out looking at microscope pictures of the boards and pondering and a lot of thought. And then we moved across to the press and peel blue film. Picked up that from from Communica actually. And we found that we had a far better adhesion to the board. We didn't have any micro breaks because there's a thin plastic coating that covers the whole thing. So the micro breaks disappeared. We could do finer tracks. And then we also switched across from ferric chloride, which is actually a nasty chemical, to hydrogen peroxide and pool acid as an etchant. We found that far more efficient, much safer, a lot cheaper, didn't go off. You could buy it from the chemist and steal some from your neighbor's pool if you don't have one yourself. And the etching time dropped from like, I can't remember how long it was, but a nice big board like that was under 2 minutes and we done and dusted. And that served us for many years until we got really creative and we started looking at having boards professionally done. So we ordered some boards from JLC PCB. The boards themselves weren't expensive. You know, you're looking at $2-3 a board. The killer was actually the courier cost to bring it into South Africa. Obviously, we can't use the post. So we were looking at about $30 for a courier to bring it in for a 1 to 1.5 kilo package. And it's not bad, especially if you're building other projects and you lump all of the boards together, you can get some nice stuff in, and the quality was really good. So we were quite happy with that. Then we started playing around with power supplies. Early on, we realized that LiPo batteries were the way to go. Because we thought we're being clever and we started researching batteries at different temperatures. And first of all, we started using 705 regulators to drop the voltage down to the 5 volts that we required for our control board. And we thought this was a good idea because the temperature inside or the temperature outside the box was like minus 61 at 30 Ks. And this, if it generated a little bit of heat, wouldn't be a bad idea inside the box. A whole lot of experiments later, we figured out that the polystyrene on the outside of the box actually provided a fairly decent insulation, and the inside temperature didn't really drop all that low. So we moved to buck converters, which were a little bit more efficient, which allowed us to then lose a battery. And then we progressed from our own built-in buck converters. You'll see on the top picture there, that was a hard impact and the whole the inductor fell off the board. And we moved to the drop-in buck converters from Micro Robotics. And that would be our final board that we flew this year, 2 little batteries and a nice little buck converter. And we moved away from huge connectors to jumper connectors or clip-in connectors that we could glue onto the board. Because one thing that we found is that this thing gets shook around quite a bit. And if your wiring is not up to scratch, it can fall off. And batteries can pop out of holders if you don't tie them down. And that's why on the bottom right-hand side, you'll see nice big holes next to the battery. And that was to put a piece of string through and actually tie everything in place. We eventually settled on longer wires instead of trying to make everything as tight as possible so that we could thread the boards without having screw-on connectors. And that really worked well. This power supply was really great this year. For our SSTV board, we used a Pi 02W with a PiCam V2. We bought some SA825 VHF modules from Nice RF, fairly decent modules. You'll see them, the blue module on the board there. And you'll see on the top, the top left picture was last year's payload. And you'll notice there's a couple of problems there. You know, there's certain things that you don't think of at the time. And if you leave it a bit late, the board arrives and then you've got to cut holes in things because you didn't look at where the connector for the antenna is going to go. And we got a GPS development board from RF Design with, I think it's a Neo 8M on it. Really nice little GPS modules, not all that expensive. It's really quite useless if you don't put it into flight mode because by default, the GPS will cut off at 10,000 meters unless you put it into flight mode, which will take it up to 50,000 meters. Board on the right was our board for this year, where we have the Raspberry Pi, we have the the GPS module, and we have the nice RF module mounted as well. The big hole in the middle there was for the RF connectors for the radio to our antenna system, and for the GPS, we just use the internal antenna on this particular one. So did it work? Yes, we got some great pictures. This was going up, and this was close to the 30-kilometer mark. Obviously, when we were sending the SSTV down, we were actually just superimposing call signs and the CPU temperature. And Christo mentioned that we had someone pick it up, the UHF transmission from Keith's payload, and that was 393 kilometers from the launch site. So really, things really seem to start working after 10 years of practice. What did we learn? Okay, so we learned that not all batteries are equal. So if the batteries are not fully charged, or you're using conventional batteries that don't work so well, we learned that the frame is incredibly important. It needs to be strong, it needs to be robust, it needs to be easy to thread the cords through the frame. I think that's a big sticking point in the mornings when we're stringing up everything together. People are battling with strings and knots and things like that. So that needs to be taken care of. Bits that stick out must be able to take the punch. I think there might be a couple of examples of that in presentations as well. But if your antenna sticks out the side and it can't fold and take a bit of a knock, you've got to watch out for that. And that's why we moved across to tape measure antennas that could really take the punch and flex and tie in knots. And that could be possibly the reason why some of the decodes weren't that great. I'm not sure if it was the receiving station or antenna was just buckled and bent. The PC boards need to be of good quality. We saw that in the micro breaks and things like that. We need to test for battery time. It doesn't help launching and then it runs out halfway. That's just not fun. The other thing that was very important that we learned the hard way last year was the boot up procedure. We all test everything at home, but what happens when there's no Wi-Fi connection to the Pi and the timer is not going to set automatically? How long is it going to take to boot up, and are we sure that it has booted up? Then very important, you've got to take that box and you've got to be a bit cruel and give it a big shake. It kind of breaks your heart in a way because you're teaching this little box of tricks with like kids' gloves hands. But when it flies on that balloon, it really gets a good shake, and especially when it comes down and it's tumbling and it's getting knotted, and then sometimes it hits the ground at about 70 k's an hour, you might have to make sure that it can take the punch. Christo mentioned as well, don't wait for the last minute. That's a huge challenge, you know. There's next month, and all of a sudden it's October and it's the week before, and it's panic stations, and it's so exciting, you just get carried away, and then you haven't slept for a week. So yeah, don't wait for the last minute, and don't be the last person. Connect your payload to the train. That's always the thing in the morning, getting things rushed, trying to connect, trying to make the launch window, and then you can't thread the string or you can't get the knot tied. So this year we actually were very proactive, and we actually threaded our balloons and put the rings on, and when we dumped it in the morning, it was good to connect and go. But really a fun experience, a great experience. Highly recommended to everyone that hasn't been there to join a launch, build a payload, and get involved. Thanks, Keith.
Thank you very much for that, Guy. And your VHF SSTV this year worked flawlessly. It was those images were coming down brilliantly, and the actual quality of the photographs was also superb. And you can compare those against the UHF SSTV, and we'll do that shortly. Thank you very much for that. I think next, I think it is Stuart ZR6 Whiskey Tango. Would you like to share and take it away, Stuart?
Yes, good evening, everyone. I'm just going to share my screen now.
And just while Stuart's busy, Stuart flew up from George and came out to Secunda to fly his payload. So last year he couriered and to Secunda, and unfortunately we didn't do such a good job for Stuart. So he came up this time personally to make sure that his Whisper beacon was configured appropriately. Thank you, Stuart.
Yeah, and thanks for doing that, Keith, last time. Right, can you see my screen?
Yep, it's showing.
Okay, all right. So I had two payloads in one, well, two modules in my payload. The first one was a sort of a standard Whisper beacon, but with a little add-on BME 280 to get pressure, humidity, because I've never measured humidity at those kind of altitudes. And also the temperature I thought would be interesting because the usual way is just to measure your CPU temperature. So, I mean, surely that's different to having an external module measuring kind of the ambient. You know, I'll get to that just now. And then my second module within this payload was a camera taking a photo every 15 seconds. I mean, I think I agree with Christo. The thrill here is to get a picture of outer space or Earth and the sort of the break from the sky, you know, the upper atmosphere and space. So, let me just get this. So before I get into my details, I just want to show a quick video, which only part of it is mine, but two others I cribbed from other people of the launch. It's just a quickie. Did that come through okay, Keith?
Yeah, it was perfect. Thank you, Stuart.
Does it have audio?
Yes, it had audio.
Okay, so right, back to my payload, which is, as I said, two modules, the Whisper beacon. And the difference here is besides sending the usual two messages, which is the first is the standard Whisper, and then a telemetry, which is what we do on the Pico balloons, I sent a third message with some extra detail. And as I mentioned, this camera taking a photo every 15 seconds. So this is the payload setup. You'll see at the top, with my mouse, yeah. This is the camera part, and there with this little clamp is the camera, which is a Pi 3 camera with a 120-degree lens, wide-angle lens. I was hoping that would give me some really good wide-angle pictures of the Earth. The processor was a Pi 0, and there's my battery, which is 1200 milliamp hours. And of course, this is 3.7, but the Pi needs 5 volts. So there was a buck boost for that, which was quite a neat little gadget because it can also take a solar panel if you have such a thing, and you can use it to charge your battery and all that, but I was just using it where the battery is connected. And there's my BM280, which is where I was going to get the extra information, which is the pressure and temperature. And the reason I wanted the pressure was that I could work out at what altitude, by doing a calculation, that I'm taking the photograph. My first thought was that the first module must send the GPS data, because it's got a GPS on it, to this one. But I had all sorts of issues, which I won't go into at the moment. So next year it'll be much better what I plan to do. So down the bottom here, we've got a Raspberry Pi Pico with a Triqueto board added to it to provide the transmitter part and the GPS. And these yellow coiled up wires is the HF antenna. And yeah, you can just see this little copper rod sticking out here, which is my GPS antenna. So going into the detail, the standard GPS module is an ATGM336H, which is and also a high precision frequency synthesizer, which is used as the transmitter. And it has two outputs, which you can configure to be 180 degrees out of phase. So that actually gives you double the output, which comes down to 20 milliwatts, which is what we use in the pico balloons. Then I also added this BM280 so I could get temperature, humidity, and pressure and calculate the altitude as a comparison to what the GPS gives me. And it was powered by a lithium polymer battery, which is 3.7 volts. So the Triqueto has the power conversion there for you. So you can supply it with 3.7 volts and it'll correctly supply 5 volts to your pico. So I transmit every 10 minutes 3 messages. The first message is a standard whisper message, which contains the usual call sign, which in this case is ZR6 Whiskey Tango. That is my sort of region 6 call sign. And then the 4-character grid square, which was, for example, Kilo Golf 43, and then your power that you're transmitting at, which is 20 milliwatts. The second message is a telemetry message, and it contains an extra 2 grid squares because I got quite an accurate GPS location of where I am. And that can be then added to your 4-character, because the whisper message only accommodates 4 characters for your grid square. So if you want a more accurate one, the second telemetry message, a second message, which is telemetry number 1, has got those extra 2 characters. And then we get the altitude, ground speed, temperature, supply voltage, and whether the GPS is actually locked or not. So if you know if it's valid. And then there's a third message, which I've got the ambient temperature, the humidity, pressure, and altitude, which is calculated from the pressure. Now, the standard Triqueto website and that doesn't support the third message. However, you can configure it to decode this extra message, which is whatever you want to send. So here is a table of the results. Now, because this thing only transmits every 10 minutes, I only have, as you can see, 8 results before the balloon crashed. So there's the call sign, and the interesting thing is the grid square, the voltage. This is the solar angle. If you were actually using a solar panel, because this is quite useful to know how much sun you've got. So when we first started at 750, it was 30 degrees, and by the time we got to altitude, it was 49 degrees. And this is the highest altitude I recorded before it crashed. And of course, there are 10 minutes between that and the next message. And there's the temperatures. Then interestingly, for those who do fly pico balloons, the second telemetry message, which is actually the third message sent, is encoded like this, which looks like junk, because I mean, this is not a valid call sign, but format-wise, it is correct. And so therefore, all the Whisper spotters will correctly receive this and upload it to the usual Whisper site. And that is the 4-character grid square and then the power level. So this is an encoding of these extra values that I sent up, which is the ambient, the humidity, pressure, and altitude. So I'll show you how you do that. So Triqueto, the website, can actually decode this, and you can put in anything you want. And all you got to do is supply this JSON script, which indicates the name of the item you're trying to encode and its units. And then you give it a high value and a low value and a step size, because you only have a total of 50 bits to encode all of this stuff. So by giving it like the step size 10, you can calculate that you don't need actually 1,100 values. You can encode it and then translate it back to what the actual value was. So if you look at the altitude, the step size is 50. So there are actually only 1,000 values there. and you're not sending 50,000 values. So the Traquita website will also analyze your JSON script and tell you what you've done here. So there you can see the ambient temperature it saw as 121 values, and this is the number of bits it would use, the humidity, etc. And as I said, the altitude was 1,000 different values, and the bits. And you feed it to, and then there was my sample, kind of looks like a junk whisper message. But it'll decode it and actually get out what you originally encoded. And that was that final one. For those who don't know about that in the Pico balloon scenario. Right, moving on to the camera and telemetry. So here we've got a Raspberry Pi Zero. And as I said earlier, the Pi camera module 3 with a wide angle 120-degree lens. And also added a BMP 280 sensor, which is just temperature and pressure. And it has a battery, and this one was 1200 milliamp hours. And unfortunately, I found out that that didn't last. So I forgot what was Guy mentioned you've got to make sure your batteries are big enough for the project. So next year, I'll definitely double that one. Okay, and the Pi Zero is programmed to perform a shot every 15 seconds. So I get the temperature, pressure, calculate the altitude from the pressure, and then take a photo and store it on the local SD card. I wasn't transmitting it. Next year, I'm definitely going to attempt SSTV. And then I add this telemetry data to, and the photo file name to a local CSV log file on the SD card. So once I recover the payload, I can then back calculate where this photograph was actually taken. So this is kind of a sample of what was recorded in the CSV file. So we've got the time slot, the time stamp, the pressure and the altitude, and then yeah, and the temperature. I thought I said that twice. Okay, so and the altitude, as I said, is calculated from the pressure. Just done this graphically. So you can see the pressure starts out pretty high at launch, which is at ground level, and it drops right down. And this is the altitude. I only recorded up to about 22 kilometers. And then the temperature is here where it drops down dramatically as well. Right, so now just to conclude, I'm going to give a short video of just key photographs, not all of them, not all the ones. If you want to see the full video, it is on YouTube, where I show all the interesting photographs, but just here are about 6, and they're 15 seconds apart. So here we go.
Stuart, I think we lost the video there.
Okay, I seem to have a problem. It doesn't seem to advance, strangely. Let's try once more. Oh, there we go. Okay, Keith, thanks. That was my presentation, and I got to thank Christo as well for this amazing event once a year, and I'll definitely be back next year. Thanks again, Christo. Back to you, Keith.
Thank you very much, Stuart. Very, very professional. All the detail in terms of those message packets that you're sending on Whisper, and brilliant photography. Absolutely brilliant photography. I'm jealous. I'm going to have to talk to you about certain things. Okay, I'd like to hand over to Hendrik. Hendrik, please take it away.
Oh, I'm mute.
Yes, you're unmuted. We can hear you.
Awesome. Now I'm also okay. I think it's that screen. Can everybody see the screen?
It's coming up. Yes, it's on screen. Thank you. Take it away.
So I was tasked with this project Aerolink, the crossband repeater payload. This is all the parts that I got sponsored by Christo to build this awesome cube. And then while I was building this thing, I got so interested in this BACAR story, and I had to make 2 cubes. And I'm going to share the other one later on after this one. So this crossband repeater cube was meant to do a few things. Do a crossband repeater setup with VHF and UHF, and as well as be able to control or set the frequencies using a LoRa module, that LoRa module over there. But I never got the time to implement it. Basically, I ran out of time because I wanted to make 2 cubes instead of 1. 100 by 100 by 100 millimeters. And then also I'm integrating the VHF UHF modules from DRA 818. It's just a module, bare module. You still need to build a PC board around it to make it work. It's just a radio module itself. And then also the LoRa module is a RFM 95868. So it's an 868 megahertz frequency which is being powered. And all of this is being controlled using a TNC 3.2 microcontroller. I did got the STM32 Blue Pill microcontrollers to get it working, but I spent too much time and effort to get the libraries for the DRA modules up and running. And then I said to myself, enough is enough. I can't waste any more time. Let's switch over to a TNC 3.2 because I had them lying around here in the workshop. So I went over to that and I got it working in less than half an hour. So it was so easy to get it working. I don't understand why the STM32 Blue Pill didn't want to work. But anyway, the TNC 3.2 is like a third of the size smaller and basically the same power requirements as the Blue Pill. Yeah, so we designed this thing to go up, and then the people can control the frequencies with the LoRa, set the frequencies, and be able to use it as a repeater. So that was the idea behind it. So this presentation is just to tell you about more about the cube's performance, and including the in-flight behavior that didn't went well. And also after the retrieval inspection, I find out why it stopped working. So the flight summary, the launch was successful. It launched quite good. Everything was up and running. Power was good. Yeah, the parachute did fail to open and free fell to the ground. And yeah, so some damage to the PC board was there. We'll get to show that later on in the thing, in the presentation. The comms duration, that was the key. It's supposed to last the entire duration until it pops, but it only lasted for 30 minutes. I successfully communicated with myself with my 2 radios, one VHF, one UHF, for the first 30 minutes. After that, it was just dead quiet, and I couldn't understand why it was quiet. I had some speculations that the battery pack or something, maybe it ran out of power or something, but yeah, after the retrieval, the cube was intact, but I lost one of the antennas. So that was one of the culprits why it stopped working. So the hardware, bill of materials of this the cube was, again, a TNC microcontroller controlling basically everything. The 2 DRA 818 modules. You can Can't remember where you can buy it, but there is a South African supplier where you can buy it and source these from. I think they go for $350 a piece, either one, the same price. And then the battery monitor, the TNC is supposed to monitor the battery with a normal voltage divider ADC read. And then the LoRa module, yeah, it's supposed to talk to a comms base station. I made the dongle for it and everything, but the code behind that piece or that part, I ran out of time and couldn't finish it in time. But for the next BACAR run, it will definitely be there. And then we have the actual base station with all the data and set points and config settings to set that repeater up. And then for the power, I use the boost converters too, because the batteries is 18650 cells. I connected 4 of them in parallel to boost the current so that I can have enough current for the DRA radios for the transmission. So those batteries worked on 3.7 volts. So I used a DC to DC to boost it to 5.2 volts for the TNC. And I needed another one boost converter for 3.3 volt for the LoRa module. The LoRa module can't be operated at 5 volts. And the DRA modules as well. It says it can operate between 3 to, I think, 4.5 max volts. So I ran everything on 3.3 volts, all the radios. The antennas, I used the Nagoya dual band antennas with the SMA connection, and I didn't use Loctite on one of the connections, particularly the bottom one. It was the VHF one, and that one screw loose with all the vibrations and stuff. You'll get to see all the vibrations and data of the other cube I captured. Yeah, unfortunately, it undid itself and off it went. No antenna anymore, and the whole thing was not operational anymore. Again, I also used the same concept like a guy with the 3D printed and carbon fiber tubes and rods, but I used 2 carbon fiber plates, like you could see in the image way at the beginning, the top and bottom, to hold the antennas, and then I just used the 4 tubes where the rope goes in for the rope attachments. And then, yeah, the post-flight inspection and findings, external condition, the cube was fully intact. Everything was, the mainframe survived the impact crash, but not the inside. Yeah, the inside was a little bit of a mess. Styrofoam box, nothing was undamaged. I just got the one antenna was back. The other antenna, yeah, I lost it during the flight, unfortunately. But once I picked up that box or that cube, I moved it around, and it sounded like a spare parts bin when I shook it. I'm like, yes, this is not right. It's not supposed to sound like this. And then I open it, and then, yeah, the entire battery pack was ripped off from the PCB because of the high G impact on the ground. It tore off the whole battery pack from the PCB. And with that, it also damaged one of the cells because, yeah, I forgot to attach or secure the batteries like Guy suggested, or with his rope with the holes. That thing or thought passed me entirely, and I didn't thought about that. So yeah, it definitely, you need to tie the batteries down. It will go out of its sockets or connections if it's not securely intact and in place. The radio status, I tested the VHF and UHF radios. They're still operational, but I don't know if I can trust it again for the next flight. I'd rather go and buy new ones and make sure they are fully operational. But yeah, the key inside the framework and electronics proved resilient, but the mechanical mounting and antenna connections, they were the weak links. And I need to redesign that to make sure everything is sturdy and connected and not loose. So yeah, the antenna detachment, like I said, caused vibration, motion, rotation forces that loosened it. And yeah, it flew off, and the repeater went offline mid-flight. I couldn't get any repeater connection anymore. The battery pack rupture, it worked perfectly fine. It's just when it crashed down on the ground, the whole thing tore apart. Everything shared. The battery connector broke off. One of the batteries side ends got also torn off. But yeah, batteries, they must be fully fastened and also crash proof. So also weight is also critical. Those lithium ion batteries, they are super heavy. With that battery mount bracket, that thing weighed a lot. It took like almost half of the weight with the battery and the homemade PCBs for that radio. That there's a lot of copper and there's a lot of weight. So I might need to think of a way to reduce that like half if I can. And then the mechanical must be first priority before of the electrical stuff, because that when I saw that, the first thing that popped to mind, it's not fail to safe. I mean, that's a big problem. If something goes wrong, every system needs to be fail to safe. So there's nothing going on, or no bursting to flames, burn a whole field down of all the other payloads if something went wrong, stuff like that. So I need to redesign and engineer that part. That's first priority for the next cube. But yeah, drop test beyond the spec. I ran out of time. I couldn't do this test. And yeah, drop it from more than 1 to 2 meters. Like free fall, like climb on the roof or a 3 building story and just drop it out the window and see what happens. If your cube survives and the electronics survives, you're good to go. Then you know that part is fully fine and operational. No problems there. And then also, I got a few suggestions from Christo about the antenna system. It's better to have a fixed soldered or potted connection. No 2-part screw-on connections or clip-on connections, because it might fail mid-flight or rip off completely. A fixed one is definitely the first prize, as well as reduce its size, like go very lightweight. You don't need heavy, big rods and stuff like that. And then, yeah, also, like I said, don't wait for the last minute. Iterate fast, fail forward. I mean, the more tests you can do, the more problems and faults you can find and correct it before the flight happens. So here's the level 2 design upgrades. Definitely going to use fixed antennas next time. Robust battery mount, definitely. Sufficient power system. Yeah, I need to redesign the buck boost thing. I can't have 2 DC-DC converters. It's very power hungry, so I need to do something there. And then also weight reduction. I really need to make this smaller, and also see if I can reduce it to a much smaller cube, 50 millimeter cube. I mean, this thing, there is a very big milestone for this thing, and if I can reduce its size, I'm going to hit one of those milestones for this project. And then, yeah, shock absorber framework that will help silicon damping pads if possible, and also the LoRa comms. I need to fix this LoRa comms, because no LoRa comms, you can't control or set up the repeater, the crossband repeater with its frequencies. You can't change frequencies. You can't set up the DRA modules for the radios. Yeah, like you can see, there's the before, the 3D printed parts. There's my carbon fiber rods. And this is after the retrieval, crash. Everything's broken inside. Battery, everything is torn off. Yeah, but here's my PCBs, also homemade. I use a laser machine for this. So I can see there's the laser machine etching all the permanent marker from the board, because I use permanent marker ink to color in the whole board. And then I give the laser machine the negative of the actual PCB. So it etches basically all the highlighted black lines. It etches those away and it leaves the white lines. So the image you see here with the black was actually white, and the white was actually the black lines on the laser machine. So once this is fully etched, I also use ferric chloride, but I'm thinking of moving over to the peroxide, the one with the pool acid. It's way faster and safer, because the ferric chloride, it just takes a lot of time. If you don't heat that chemicals up, it will take forever to etch your boards. And yeah, this is how the board looks like with the 2 radio modules on connected. I missed one of the tracks. You can see there's a green line. I modded that in. After I did some tests, I just like, why is this one not working? And I look at the schematics and I'm like, oh, yes, I forgot to add this track over here. So I had to do a little wire mod over there. And what you see over here is it's low pass filters. So this radio doesn't have a low pass filter. So I had to add low pass filters for each radio. And yeah, that took some design to get that right. So then it's safe to operate, no harmonics. And then also I specifically added this track in the PCB like this with the copper away. It's for the RF, so the RF don't get mixed on the ground plane. And also around these areas, I had stitching, like you can see in this image over here. I did via stitching over here to connect the grounds together to make sure there's no floating grounds whatsoever all around this area. And the RF line is nicely centered and far away from the ground, so it doesn't interfere with my digital signals or my voltage plane. But yeah, this is how my cube looks like, empty with no electronics inside. There's the battery pack. So one of these batteries got torn open on that side, and this thing was shattered, the battery holder. Yeah, there's the STM Blue Pole, the original one, but it got replaced with a TNC. This is the LoRa module that I used, and this is the two boost converters. So this first one is a boost converter to 5V2, and then I took this 5V2 2 amps to another DC boost buck converter actually that takes it to 3.3 volts at 3 amps. And a nice big ground plane, and this goes all the way to the LoRa module, and these power pins over here gets tied into with a connector, as you see in this image over here. That's your power cables, goes to the next PC board for the DRA modules. Yeah, this is another picture how it looks like the aftermath when it hit the ground. This is the KiCad design files and some more images of the battery pack of this cube. So yeah, I don't have any regrets with this. There's a very steep learning curve. I was quite into the deep end with this BACAR thing, but I really enjoyed the challenge. It was very challenging. I'm not joking here. I had a lot of hair that I pulled out of my head, a lot of late nights getting this thing run because the clock was against me, partially my own fault because I had to make 2 instead of 1. But it's a lot of fun and educational, and I'll definitely be back next year with lighter, tougher, and smarter one. So yeah, this first one is a proof of concept, and it did work. It didn't work long enough. So we want to make this thing work long enough so that we can actually use it. And yeah, version 2, like I said, will be smaller, tougher, and stronger. And then yeah, this is the Project Aerolink repeater cube. So basically we extend the communication to the edge of space, 1 cube at a time. It's basically what this is for, to extend the communication for everybody. So this was the Project Aerolink cube presentation for this cube. And then I can go on to Lumina Stratos project. And this is my own scientific cube that I wanted to make with a lot of sensors and stuff, because this was my first run and I wanted to capture as much data as I can using this cube. So this cube's purpose was just sensor and a bunch of sensors and taking measurements. So yeah, it completed its flight. I got a recording of 28 kilometers in my logs, and it was very awesome. I was super impressed with this because this project, I didn't do a PCB. I ran out of time and I couldn't make a PCB or a Veraboard to put everything on because I saw how heavy it was. And I'm like, I've got so much sensors. It's going to be super heavy and it's going to go over the 500 gram limit. So I went to make a bold move and wired everything on a wire harness. It looks like a rat's nest, but it worked. It worked. There's a few minor flaws, but it worked. And I was super, super pleased with the results. But yeah, it was partial operational. Again, it's supposed to have a APRS tracker, a 2-meter APRS tracker. Ran out of time, couldn't get it done. Also, LoRa system 432 something for a base station for real-time data transmissions. Didn't get it to it, so that's going to be added for the next time. So yeah, this is the overview. This is all my hardware that I used for this cube. The main controller was a Raspberry Pi 02W. I wanted to use 2 controllers. The Raspberry Pi 02 was for the photo and video captures, and I wanted to use an ESP32 dev kit for the rest of all the other sensors. But as I said, time was out of the essence, so I had to make some compromises. So I slapped everything onto the Raspberry Pi 20. Data logging, sensor fusion, camera control, basically everything. So I also used a real-time clock for timekeeping, but it failed. I forgot to sync it. with the time. So all my times on all my data were wrong. So I had to modify the timestamps just by looking at the pressure sensor on or the altitude sensor to get the exact timestamps thereafter, and just adjust the time settings accordingly to plot the graphs. I use the GPS module, the uBlock 7. It's a USB module, but I connected it to the Raspberry Pi. It did connect and give me data, but it never tracked. I don't understand why it didn't track. It never got the fix. I think it got one fix of the entire flight time, one singular fix position. Yeah, so I need to look into this or change this GPS entirely with something else. But lesson learned on that: don't use a USB uBlocks thing. Yeah, it's struggling to get a fix. Anyway, I used 2 temperature or humidity sensors. I used the high spec one on the outside and a DHT22 one, that white cube one for the inside, to check the differences between outside and inside temperatures. But in the code, because I rushed time, I didn't label these clearly, and I got confused. When I look at the data, it didn't make sense. I got sensor readings, but I can't make use of it. I don't understand which one's outside, which one was outside. So that's a lesson for the next one, for the next BACAR thing. I also slapped on a UV sensor to measure the UV as I go up, if it's going to be higher, more intense or less intense. I don't know. I got a UV values, but I got some values, but again, I don't know what it means. I didn't have time to process everything. I basically just slapped on the sensors and measured all the raw values. And then afterwards trying to draw up some graphs and do some post-processing with all the values, as you'll see later in this the presentation. So yeah, I measured the battery voltage as well. I was supposed to measure the battery current, but I didn't hook up the sensor, the INA 218. After I opened it, I looked at the sensor. I'm like, oh, yes, I never connected the battery to the sensor. So the sensor was never used, forgot to connect it. I was so sad when I saw that. I also use a pressure sensor, a compass to the magnetometer. I saw someone in chat asked about magnetometer measurements. I did that. And yeah, that's very busy. I don't know what to make of that readings over there. You'll see how busy that magnetometer is on how that cube spin actually up there in the sky. And then yeah, camera, I use a camera Raspberry Pi module. I think I used the version 1.3 camera with the small lens. And I made 2-minute recording videos. I didn't do images. I did video recordings from start to whenever the camera died. And I didn't do any pre-processing on the videos. I left it as .h264 segment video recordings, and then afterwards I'll just convert it on the Pi system for MP3 or MP4 files for viewing. And I did share this on my the Google Drive, so you can check all the videos there. Power source, yeah, I went extreme and slapped on a 5,000 milliamp hour battery, LiPo battery onto it, and that battery was still, there was enough juice. It was I think 3.5 volts. Afterwards I've measured it. And yeah, everything was still running. After the payload crash, I could still hear the buzzer beeping as they took out everything in the clubhouse. So yeah, it definitely had power, but more on that later. And yeah, structure, same structure as the, the crossband repeater. It's got the exact same structure or format for that as well. So yes, the signs of life, what I mean about that, the buzzer was activated every 5 minutes. And that tells me it's a heartbeat, it's online, and as well, it's audible cues to let me know stuff is running, so I don't need to guess. Yeah, so after the impact, it was still buzzing, doing its thing, and I was like super excited. I was like, yes, this thing is still recording, but it didn't. So yeah, the system was running, but like I said, it can mean a few things. Upon opening the cube, the heartbeat LED was still active. It pulsed with the buzzers and stuff, but the Pi, I could not access the Pi with SSH after a power cycle was done. So I have concerns about this. But yeah, after I look at this Pi was, yeah, it was severely damaged. I don't know what caused that problem. I don't know if it was the high impact on the ground landing or after the balloon popped and it was on its way down. Something happened on this Pi. Yeah. So post-recovery status, the physical damage. So the damage here, the Pi was so hot you could barely touch it. So there was definitely a short on that system. And also it bent. It looked parabolic. It wasn't straight. The PCB wasn't straight. It was half curved. So that thing was super warped. I don't know how that happened, or maybe it was the extreme heat on the board because of the 3v3 short circuit. But after I look at this 3v3 short circuit, the micro SD card was cracked, and that caused the 3v3 short on the Pi, and that was the reason why it got so hot. And also, there was a wiring chaos. I didn't use any PCB. There could be happening a lot of problems there. It could be anything, or the wires or something. I don't know. But yeah, like I said, it was a life choice I had to make up time during the building process. So, but the root cause was the lack of PCB, thermal runaway, and the SD card crack. There you can see images of the crack of the SD card right through in the middle. It actually bent this whole SD card holder. You can see it's cracked there at the bottom. After I removed it, the short was done. I could boot up the Pi, but I still couldn't SSH into it because the Pi kept on rebooting. So that warp Pi, I think there was some dry joints and stuff happening there. But there you can see my harness. That's how it looked like. I've got a USB on the go cable for the GPS module. This is my power supply. USB cable goes to a boost converter to the actual LiPo battery that gives this whole thing power. And there's my harness mesh with all my sensors and everything. The TNC was in here for the voltage measurement as well as the UV sensor, because the UV sensor was also analog. Yeah, and there was the photos of the whole payload train. Parachute here, parachute there, and there's my two cubes, those two blue ones. I think this was Lumina Stratos, and that one was Project Aerolink. So what actually worked on this Lumina Stratos cube? The video recordings. It recorded 32-minute video clips that was captured. I was very pleased on this. But yeah, it was stunning. I could see the Earth curvature and the horizon glow. It was so cool to look at it. I'm still watching these videos, rewatching it. I can't get enough of this. This videos was so cool. But unfortunately, on the way down, I think the first minute or so, the Raspberry Pi seemed to malfunction. It could be the heat or something, but there's no video after that. I would have loved to see the video when it hit the ground, but yeah, the Raspberry Pi, I think it got too hot or something malfunctioned on the way down. So I only have the ascent video footage, but not the descent. So the sensor logging, I logged UV index via the TNC, the battery voltage, acceleration, gyro, the magnetometer, all 3 axes on that. I measured the pressure and the altitude, temperatures, and the humidity. So what failed in this, after I inspect the rat's nest, the GPS didn't work at all. I looked at the GPS data. It was a total bust. I don't know what happened there. The RTC, I forgot to sync the time on that. Because of this, all the timestamps on my data was incorrect, but I still have the data, so I had to make use of it somehow. And the temperature and humidity labels, I have to make double sure I label the things correctly, which is inside, what's outside, as well as in the code. In the code, I didn't specify which one was outdoor and which one was indoor in the cube. And you will see in the graphs how confused this data will look like. But yeah, despite all these issues, and I used the relative time deltas for this to allow for some data how can I say, plots. So there's my data highlight of the plots. So what you can see here is the UV and the battery versus time. So the yellow one is the battery. That's how the battery voltage look like. And the purple one is the UV measurements of the UV board that I've captured. So yeah, there was all the time flights. And I think around just after 9, somewhere here, the balloon popped. And I think this was when it hit the ground or something. But you'll see on the G-force, the data plots as well. And this is the tilt versus the time. I measured the tilt with the gyroscope, the MPU 4060 or 6040. This is how much it tilted during the flight time. This is the degrees tilt, and also on the time, how much it tilted during the flight time. And this one over here was vibration versus time. So there was a lot of vibrations during the flight time as well. And this is the vibration level. The highest one was over here. I don't know if that was the impact it hit the ground or something, but I don't know. Like I said, it was difficult for me with the time because my time was all wrong. So I had to guess what on the graphs what happened. And here's my pitch, roll, yaw versus time. This is the accelerometer gyroscope combination. Like you can see, the pitch is blue, the roll is green, and the red is the yaw. So there's a lot of activity while it's flying in the air, while it's ascending. There's a lot of movement. And this movement over here, I think this was captured while the Hamnet was transporting the cube back, because they arrived somewhere around here, 11:30, close to 12 o'clock, somewhere here they arrived. So I think this is when they picked up all the mess and gooid it in the bucket or something. You can see stuff going on there. And here's the G-force and the vibration versus time. The G-force is the blue line, vibration is the purple line. Like you see, there's a vibration. The G-force, you see there's the flat spot. I don't know if this was when it was lying on the ground or something. And that high spike over there could be when it was hitting the ground, 2.5 Gs. I don't know. Like I said, it's difficult at the time. So all this varies is based on estimation, but I have the data, so why not show it? I mean, it looks very interesting. There's the G-force and altitude versus time. Like you can see over here, the green is obviously the altitude, how it climbed. There's the altitude markings on the right-hand side. You can see 25 kilometers, it went up all the way. So somewhere around 28 kilometers, it popped, and you can see how quickly this thing fell down relative to the time. This thing was speeding, and then it hit the ground here somewhere. Very cool and interesting. I like to watch these graphs. You get so much information. And here's the total mess up of the temperature and humidities. It's all over the place. I don't know what's going on here, but I can tell you my sensors bottom out at -40. That's how cold this thing captured it. Past -40, almost -50, somewhere there. The temperature indoor or outdoor, I don't know which one, but I think these are swapped. So the yellow one, I think, is the indoor one inside of the cube, and the red one is the outside one. And here, the temperature climbed rapidly. I think this is when it was lying in the sun. Yes. You see, there's the outside one. I think the yellow one should be the inside one. But this temperature was rising rapidly. And that's when I switched the device off, somewhere around here. And when I saw the temperature, so this thing was cooking. Like I told you, the Raspberry Pi, I could hardly even touch it. So yeah, and the dotted lines is the humidity of outside and inside as well. How the humidity look like in the air. Very cool. And over here is the cumulative displacement versus time, also using the MPU 6040 IMU sensor. So you can see, I don't know how accurate this displacement thing is, but here's the time setting as well. This is what the sensors was measuring or capturing. So blue is your east, Y is your north, and Z is your up. This graph doesn't make sense to me, but it's interesting to see how it captured the data. Then another one, yes, the compass heading, the magnetic stuff. This is also, that's from that magnetometer. So yeah, this thing moved around a lot. Here's the heading in degrees on this left-hand side. So this thing went all over the place. Even if you look at the videos, you'll see there's a lot of movement on the cube on the videos. I can't believe how much that cubes move up there. Even at the verge of where the balloon pops, it still moves a lot. But yeah, it's interesting to see this compass heading, how it looks. I assume this little section over here is where it was lying on the ground, because there's not a lot of movement going on over here. But a lot of movement while going up, and then when the Hamnet recovered it, that's that, and then club, switch it off. There's the angular position versus time, also the IMU sensor, the angular position in degrees. That's how it looked like. It's X is roll, green is pitch, and Z is yaw movement of my cube while it was moving in the air. Super cool. You see the roll, X is rolled. I don't know if my sensor was upside or oriented correctly, but I think the roll is my actual left and right movement, maybe. But yeah, with that RatsNet connection, it's hard to tell. Key points for next one, use a PCB. to get accurate data, not just data. And yeah, this is my altitude and pressure versus time. This is really cool. I love this graph a lot. I have made screenshots of this graph, and I keep looking at this because it's so interesting to see. So the blue is altitude and the red is the pressure. So as you can see, as it goes up with altitude, you can see the pressure drops. So you can see here, it's almost at zero Pascal. That's how close it is to the near space. That's ridiculous. It's insane. And when the balloon popped, you can see it's quickly climbing back up as the fall. I really wanted to see what this point looks like with the data, but yeah, I don't have any timestamps. But for next cube, I want to see this cross-sectional areas and what the data on that looks like. Yeah, very cool graph over there. And here I've got angular velocity and linear acceleration magnitude versus time. So the blue one is the angular velocity, and the purple or magenta, that is the linear acceleration of the cube. So yeah, this is while it was ascending. And over here, I assume when it fell on the ground, lying in the sun, this is the Hamlet recovery back to the clubhouse. And that's when I switch it off. Angular velocity is insane. Yeah, it's rad. The angular velocity is rads per second, and the linear acceleration is meters per second square of the acceleration. Now, this acceleration spike doesn't make sense over here, what the spike is. I don't know what this is. But this one could be when it fell or something, I don't know. But yeah, I got data, but yeah, lessons learned. No PCB, it's a huge risk because you just get data. Like the IMU sensor, it's not oriented in the correct position relative to the cube's position, so you don't know what data is what. And also you need proper power rails, not just wire mesh. RTC backup, definitely. Get that RTC working, sync the time, and also make sure your GPS is set up correctly and also set into flight mode. Otherwise, it won't work. Thermal runaway, definitely. I must add some heat sinks on the Pi, or make sure there's no shorts or something I can make shorts, prevent shorts, or manage ventilation and airflow to make it cool down if it's a certain temperature or something like that. And also the SD card. Someone on the group said you must place this SD card in like a sturdy retainer or an enclosure to prevent it from any breaking. So if you have any backup SD cards or something, yeah, that's a good thing because I saw mine cracked. And luckily, I didn't save any data on that, so I'm good. I'm very lucky on that. GPS failure, yeah. Test pre-flight. Make sure the GPS can work at high altitudes as well. Put it into flight mode. Don't just use it like me. I didn't even know you can do it in flight mode, but yeah. RTC drift, yeah. My RTC wasn't synced. I need to sync it, or I can sync it via GPS if the GPS is working, of course. Or you can use NTP type connection on the Pi. Set up your phone or your laptop as a hotspot. Just let the Pi connect on it and auto connect or sync your time via the internet. And make sure the coin cell is also properly installed because mine was a little bit loose. I think that might also be a problem. And then also sensor labeling is a huge, huge thing. Make sure all the sensors are labeled clearly and correctly so there's no confusion. And I want to fix my low route downlink for the base station to get real-time telemetry data. As well as the wiring, try to eliminate all loose wires because it can cause issues when it fell or hit the ground or whatever the cause might be. So plan for version 2. I want to add overlays for the data on the video capture. And then also I'm playing with the video capture and imaging to do both at the same time, but same time in quotation marks because I want to alternate the video and still image captures at different time intervals. Like if I finish my 2-minute video recording, do a quick still image capture and then go back to the 2-minute video recording and repeat that as many times as you need. Then also use a PCB, maybe use a film PCB or a small thin PCB types. You get the small PCB types from JLC PCB. It's very lightweight. Maybe think of that. They also clearly label the sensors. And also I want to add more sensors. I mean, I don't have enough sensors. I need more sensors. There's more unknown stuff I want to sense and capture the data and graph it. And yeah, fix the telemetry downlink because that's also a good thing to have. You can monitor the cube as it goes up and down and see what's going on. and definitely upgrade the antennas. I want to make them smaller and more robust. I don't want to use SMA again. I've learned my lesson with that. No more. I don't want to use that anymore. Then remember to sync any time modules or GPS modules that I have on that cube. And then basically the conclusion is, despite the GPS, wrong timestamp, a bent Raspberry Pi, this project delivered unprecedented video footage of entire ascension. I'm very pleased with that. I'm still watching, like I said, I'm still watching it. It's so cool to watch. Rich sensor data set for post-flight analysis. That's also cool to have. Proof of concept. I know this thing worked despite my design choices and my decisions. I did get a bunch of data out of it, but it's just data. I don't want data. I want to have valid data so I can make sense of it. Yeah, the beep buzzer still beeping after impact was so hilarious. It was more than a sign of life. It was a symbol of resilience. I'm working. I'm still there. So yeah, we didn't just fly. We learned a lot. So the final reflection is, this was not a perfect mission, definitely not, but it was a successful one. The data, the videos, the graphs, the stories from this flight will feel version 2 like really hard, smarter, tougher, more capable Illumina Stratos cube. So yeah, thank you again for the BACAR team, the Hamnet team. Thank you again for Chris too for organizing this event, and Keith for all the communication. This was really cool. And yeah, this is me, ZS6HGH 73. This is Project Illumina Stratos, and with this cube, we're measuring the edge of space, one cube at a time. So that's it for my 2 cubes. Back to you, Keith. That's all from me.
Thank you very, very much, Hendrik. Yeah, you were very ambitious with 2 cubes. When you hear my story, 2 cubes in the time frame, well done. And you've got an amazing set of data there, and I have watched your video. I get drunk watching it because of the movement of the cube, but it's a brilliant video, and also the quality of the imaging was awesome. So there's a lot to go with the Raspberry Pi and the camera on that side as well. So very well done on your missions there, and for sharing that, Hendrik. I look forward to next year flying with you again. Okay, you can stop sharing, Hendrik, and then I know that we're very over time, everybody. I under-anticipated how long these little presentations would take, but if you like, we can continue. And just, I think there's 2 more presentations to do, but I'll keep mine very, very short, or hold it over for another time frame, just to not delay everybody, because I know it's getting late. Thank you, Ray. I'll keep going. So Nathan, if you don't mind sharing your presentation now, but do keep it short. We are getting late there, Nathan. Thank you. Nathan, are you going to share? Nathan, we can't hear you. Okay, Nathan, let me go into mine again, and we will come back to you shortly, so as not to delay further. I just want to get to my presentation. Where are we? Okay. So we'll move forward. So my presentation is all about the UHF SSTV transmitter. And this has also been and I mentioned to you that Christo actually set a challenge, and he set it last year, 2024. And he says, Keith, yes, you put a Fox transmitter on your 2023 flight, which was a simple little thing. But why not do a SSTV, UHF SSTV for the 2024 flight? And And I thought to myself, well, I've got some club members in the Sandton Amateur Radio Club. They are gurus at programming and playing with microprocessors. They certainly will help me do this. And then they were just unfortunately far too busy, and Keith had to try and do this by himself. So be aware that if Keith can get it done, anybody can get it done. So the UHF SSTV transmitter flew for the first time in 2024, and then it was enhanced and it flew again in 2025. I'm not sure though, Christo, if this is good for your BACAR train, because both times the SSTV is flown, the parachute hasn't opened. So maybe there's some correlation there that I'm unaware of. But firstly, the technical objectives. I wanted to do data collection on this particular flight. So I added a GPS module and a BME sensor for altitude, speed, date and time. Then obviously we had the SSTV radio transmission, and last time I was sending fixed images to the ground station and recording other images on the SD card. This time I wanted to alternate between sending fixed images and from the SD card, as well as live camera images, and then sending that over the SSTV transmission, together with sensor data overlaid on those images. So my design considerations: I wanted reliable image transmission. I wanted low power consumption. Everyone's talking about batteries. I'm a bit of a Heath Robinson or amateur radio operator. So being emphasis on the amateur. You can see those professional circuit boards that some of them make. Well, have a look at my payload and you'll think, well, absolutely amateur. And Hendrik was talking about wiring harnesses. I'll show you my pictures now. But I was always worried about the battery and whether it would last for, my mission time was about 3 hours in case the payload flew for 2 hours. And so I had to decide between 0.5 watt transmission or 1 watt transmission. And obviously 1 watt consumes battery power a lot faster. And I've always had this concern, probably like driving an electric vehicle, whether it's going to last long enough. So I transmitted on 0.5 watts in the 2025 flight. As has been mentioned, our payload had to be under 500 grams and fit in the CubeSat profile, and ideally be reusable. I don't like to break things and throw them away, and having spent the money, I'm a bit of a Scrooge, and or you can say cheap sometimes. So I wanted it to be absolutely reusable, and I did reuse some of the parts from 2024, and I wanted it to be inexpensive and simple. As Hendrik mentioned, it does take time, and I think it was also mentioned by most of the other operators, it does take time to put your cubes together and to test them adequately, so it had to be fairly simple and inexpensive. So I used the SA828 transceiver module, which you've seen earlier in this presentation as well. I used one that I used in 2024, and there on the image of this module, you can see it's got a rotary switch where you can select from 16 channels. Well, in the 2024 flight, that popped totally off the board and it wasn't there any longer. So I had to fix the channels that I was using, and that option is no longer there on the particular board I used, but it did work very, very well. These transmitters are relatively inexpensive to purchase. You're looking at about between 200 and 350 Rand, depending on where you get them from, and courier landing costs and so on. And there also is one without the connector fitted that you can purchase. I think that's the SA818, and it's an excellent little module. You can program the frequencies. You get one for VHF, you get one for UHF. And there you can see the connections on the particular module that I used. Obviously, we had VCC, your power, we had ground, we had the antenna connection. So that was a screw-on SMA connector for the antenna connection. Then I used the external microphone positive, and I'll get into more detail right now, but I sent the audio into the mic input, and the mic negative was connected to ground. I connected the high-low for low power, so that was connected to ground for low power. And the PTT, the press to talk, so that's a GPIO pin from my processor to activate it when I wanted to transmit, and then to stop transmitting at the end of the transmission to allow the transmitter to cool down and to save battery power. And then there is a chip select, as I call it, and you can put the chip into, or the transmitter into sleep mode, where you can save a lot of power. I did not have a GPIO pin available to do this, so I just tied that into permanent high for normal operation mode. I thought at one point I could ground it and then just activate the PTT and it would override this, but it unfortunately didn't on this particular module. So I had to just put that into tie the CS pin high for normal operating mode. So it went to receive mode after the PTT was lifted every time. And there you can see a simple circuit diagram of that PTT being my control pin on it, and the mic input to receive my audio signal that I was sending it. I had a GPS module. This is the GPS module I used. It's using the Neo M8N chipset. It's a U-Blox chipset. And unfortunately, I didn't know enough about GPSs. I wanted to operate on the I2C bus port, which is a SDA, a data line, and a clock. And I didn't want to use the UART because I had another sensor as well that also operated on the I2C port, and I wanted to connect them both to the I2C bus because I didn't have enough pins to operate this one on the UART pin port of the microprocessor, and then still have 2 pins for the I2C bus. It just was not possible with the way I'd configured the design. So on this particular GPS, I used VCC ground, the data line, and the clock line, and not the UART. But if you've got a UART free, you can certainly talk to it continuously via the UART as well. You just can't have any other sensor or processor on the same UART. You can't share that. I used an 89850 DDS module, so a direct synchronous module to generate a sine wave. So just why did I use this particular module? Last year, when I was building the first SSTV module, I tried to use a pulse width modulation output, a GPIO pin for pulse width modulation, and then to smooth that using a low pass filter, not a low pass filter, a low pass filter. But the quality of the images coming through the transmitter was very poor. And then I did a little bit of research, and I did see that other persons had used the DDS, which generates either a square wave or a sine wave or a triangular wave, depending what you want. You can program the device to do that. You control it through registers. You tell it what frequency you want to, you set the frequency in the registers, and then you give it an update pulse, and it will load that into its output, and it will generate the sine wave at that frequency for you. So it's a fixed amplitude sine wave that comes out of it at the frequency that you want, which is what I then did. And using the DDS, you get beautiful sine waves fed directly into that mic input of the transmitter, the SA828 transmitter, and the transmitter is very happy with those sine waves coming in, and it makes beautiful SSTV images. So that's what I did there. One thing to note, though, on the SSTV, I'll get to the programming now. The standard timings using on your microprocessor, you might have to adjust those standard timings. So the 9850 is commonly available. It costs about 350 to 400 Rand, but you require the following pins: a VCC and ground, obviously, then 3 GPIO pins. And I was using the ES32 microprocessor. So that's for the clock, the update, and the data line to control the DDS. I tried to control the DDS and share these pins with one of the I2C bus at times and alternate between them, but I wasn't that successful with that, so I dedicated these pins to it. Quite often, you'll notice that in the literature, they talk about the reset pin. but you do not have to reset the 89850 DDS module. You can tie the reset pin either high or low. Can't remember exactly what it is, so that is not in reset mode, and you just control it with the clock and the update pulse and the serial data line, and it works perfectly. I chose to use the ITC bus, as I mentioned, because I wanted to share the BME 280, as mentioned by some of the other flight payloads. I also use the BME 280 sensor. There is an image. You get the BME 280 sensor. You can get the 4-pin version or the 5-pin version. I use the 4-pin version, so it's got your power, V in and ground, and it's got the I2C bus, the clock and the data line to communicate with the BME 280 sensor on the I2C bus. This device, unfortunately, the one I purchased, was only rated to about 12,000 meters. So I did purchase an alternative high altitude version rated to above 30,000 meters, but I left the existing one in circuit, and it seemed to work perfectly for BACAR-13, other than I was calculating the altitude, and that was a little bit suspect. And we'll talk about that now. As my microcontroller, I chose to use the ESP32 CAM module. It's got a built-in camera and a on-board SD card. And there you can see the GPIO pins that it says are available. But you don't have all these GPIO pins available because they're used by the SD card and or by the camera. So you only have these ones that I've circled available. And to even use this number of GPIO pins, you've got to place the SD card into 1-bit mode, which is not an issue. It works perfectly in 1-bit mode, but you've got to be very careful how you use your GPIO pins. You don't have that many available to you. There you can see the UART and the 2 pins that were for the UART. If I had dedicated those to the GPS, then they would have not been available to use on the I2C bus. And I needed these 3 pins to control the 89850 DDS. So going forward, I like the little ESP32 CAM. It's very easy to program, very easy to use, and it's robust. I've even offset, when I've put it into the socket and taken out the socket, I've offset the pins, taken it out, put it back in properly, and it still works fine. So it hasn't blown up or done anything like that. So it's quite a robust little ESP32. One thing I did note, there's a ground pin over here. If you take this ground pin to ground, you would think you have to. If you take that pin to ground, then the ESP32 will refuse to boot. So that pin, I think it's this pin, it's either that one or this one, but I think it's this pin, as I've indicated here. Do not ground this pin, otherwise the ESP32 will not boot. The ESP32 comes with SPI RAM on it. Make sure if you use the ESP32 for image work that you do get one that contains SPI RAM. And there are some Chinese versions which have a PSRAM on them, PSRAM on them, but they don't seem to want to work with the Arduino IDE and the libraries. So you need to get PSRAM that is I think a spec, I think it is on it. So there's my payload. There you can see the GPS, the transmitter. I did not use the antenna. I put the antenna there on, so I just don't power this baby without an antenna. But I did not use that antenna because a colleague of mine, Matthew, ZS6MDX, who's had previous flight experience, says this is a weak point. It will just snap and break. You saw how the payloads got dragged along the ground before they got airborne. That's a weak point. So I have a cable that connects between the UHF, just RG58 or RG, what's even the thinner one, that connects between the transmitter and the antenna. And there you can see my antenna. It's a UHF dipole at a 90-degree angle, the 2 legs, and it connects through RG58 to that SMA connector. I've got a switch on one of my first payloads. I plugged the battery in and out, and you have to then screw on the payload and everything, and the string is waiting for you to get connected to the balloon, and you holding them up. Now all I do is everything's configured, it's locked in the box, everything's screwed down, it's enclosed, taped, and all I've got to do is activate the switch, and it will go into, it will power on and continue. There you can see the ESP32 cam board with a piece of Euro board and the camera on a flexi lead, which connects to a hole in the frame. There's the DDS, and you'll note that I used a commercial available power bank to power my module. I think and it's been pretty robust to do that, but it is weighty. It's about 240 grams and takes a bit of space in the payload. And with the plugged-in connector here, that's a lot of space that you've got to make do. So I think going forward, I'm also going to go with the lithium batteries. Finally, programming. I'm not a programmer, but I used AI help, and that came in very, very useful. I used the Arduino IDE to program the ES32 board, and I used AI continuously, Copilot AI, to say, okay, I want to do this, Mr. AI, help me here. And it was very good at helping me. You've just got to be careful what version of the Arduino IDE it is using to give you the libraries to use and so on. But I have learned an enormous amount of coding this the package. Tip: when programming the board, remove the SD card. I found that it would not go into programming mode consistently if I didn't remove the SD card. Be careful when lining up the pins on the ES32 board. So it's easy to offset as you put it in. My vision is not what it used to be, and I occasionally offset the pins when I was taking it in and out of the test jig. So be careful of that. It might be worth just putting a longer connector on that it can't offset against. And I alternated between two ESP32 GAM boards when I was programming and testing, because it takes a little bit of a while to compile and to then test, and you want to make a quick change, and you then can program another one, and you can just switch them in and out. Because testing, I was using Martin 1 format as the SSTV, and it is a transmission is 114 seconds. So if you want to get through a full transmission, and then you want to alter something or getting through a few transmissions, it takes time. So I alternated boards, and I mentioned the UART pins. So I couldn't use the standard UART pins for debugging because they were connected to the I2C bus. So I used the Arduino Kitty terminal server and Wi-Fi over the air, and that worked very well. And there you can see the debug print line, which is different to the normal print line. The debug print line goes over Wi-Fi to Kitty terminal, and I can then get all the debugging information from the ESP32, which helped enormously. Then payload, bill of materials. I'm going to go through this very quickly. I know we're way over time. ESP32 8090 DS, the BME 280 environmental sensor, the GPS module, and it looks like I better change that GPS module. I made exactly the same mistake as many others. I wasn't aware that it had to be put into flight mode, and even then, if you do put it into flight mode and it receives an acceleration of over 1G, it will then disable providing you the latitude and longitude coordinates, and the altitude, it totally disables it. That's one of the conditions of some of the commercial GPSs, that they've got to conform to a particular spec. And unfortunately, I can't promise you that we won't exceed 1G on acceleration up off the ground, and even when it's swinging around at the sky and when it starts falling. You can use any of those UHF modules, a power bank or other 5-volt source. I had lots of interconnecting wires. I used JST connecting wires this time around. Those are the wires last time I soldered them, but these proved to be pretty robust. The JST ones, I've used DuPont wires previously as well, and they also worked. A piece of Euroboard, and then a 3D printed or laser cut 100mm cube. The laser cut one is a little bit heavier than the 3D printed one, so very big thank you to Matthew ZS6MDV for printing the 3D board for me. And then obviously the stainless steel rings that Christo mentioned, and they're very useful to interconnect the payloads. Optional upgrades, I would use a different ESP2 CAM boards. There are new ones coming on market, which have a USB port integrated on them. like this one over here, you no longer have to use a little programming board. I would potentially extend the number of GPIO pins I've got using a 8574 or 8575 module. I actually bought one. I've got one of these, but I didn't use it. I also ran out of time to implement additional GPIOs, sorry. I would also suggest that you use a longer cord for the camera, and I would improve my camera quality. Not going to go through the slide. We're running out of time. There you can see some of the results of the images. This is, I decided to point the camera downwards on this particular flight. Last flight, I was pointing it outside of the side of the cube. And there you can see the first image and the overlays that were being printed on the images with the GPS showing me a 0, 0. It was not in flight mode, so I don't have the altitude and the coordinates from the GPS, nor the heading and the speed. But it did give me the date and the time at least. And my BME sensor was providing the temperature, the pressure, and a calculated altitude. And according to my altitude, the payload went to 46 kilometers above the surface. So there is some flaw in my calculation, and also providing the humidity. So the images that I've got all looking downwards, and you can see the payload in the string below the ESP32 cam board. You'll note telescope number 3, telescope number 4. These were the fixed images alternating with the live images that were taken. Then I'm not going to go through that. We've spoken a little bit about that. And so future enhancements, I'm going to store the data on the SD card. I only overlaid it on the images this time around. I will use a different GPS module or make sure that it's in the right mode. It works perfectly on the ground, but as soon as it took off, there was no data. And I would make sure that the altitude calculation is a lot more accurate and use a higher quality camera. Transmission, I also want to use lights. I know that Guy, ZSXGUI, and his team were using Robot 36 color mode, which transmits in 36 seconds an image. I was using Martin 1, which is a higher quality image, but it takes 114 seconds. So would like to implement the Robot 36 as well. I'm thinking of implementing voice transmissions, so data over voice. It would enunciate synthesized voice, giving you the sensor data. I'm going to implement APRS telemetry, CW transmissions as well, giving data information over CW. I thought that might be a nice to have as well. And hoping that these things will encourage others to participate in BACAR at a distance. Okay, and I might switch to a Raspberry Pi because the camera quality and processing power of the Raspberry Pi is superior to the ESP32 cam board. And I'm currently using the payload for other things like RDF, fox hunting, and JOTA as well, which is the reusability quite nice. And as has been previously mentioned, the parachute recovery didn't work, even though Christo had a second standby parachute on this last flight. Because of 2024, the parachute didn't open. Unfortunately, something went wrong and the parachutes didn't open again. And there you can see the pressure pop and recovery. These are the images that were taken by, I think, the Christo's payload right at the top. There's a balloon starting to pop, and there's no instruction to descend. I think that Christo has indicated previously that you can instruct the payload to disconnect from the balloon if it's now going into restricted airspace and you want it to descend. But this, under normal circumstances, it reaches an altitude where the pressure inside the balloon just gets so great that the balloon pops. And there you can see the sequence of those images that were taken. So very well done to the team there. This is the team that recovered the payload. So there you can see they tracking it. The Hamlet team, so thank you very much. They do an excellent job of tracking the payload. And there you can see everything that they found lying on the ground. Okay, sorry. And there are images available for those that are interested in, videos, Stuart's payloads, and there's some other YouTube videos that have been made that are available on things. So my conclusion, thank you to everybody who was involved. It's an absolute adventure. I thoroughly enjoy participating in a BACAR. At this point in time, I'd like to stop sharing and just say, Nathan, are you ready? And please, Nathan, we're running badly over time. If you
All right,
can.
I'm ready. I'm going to screen. Let's get cracking.
Go ahead, Nathan.
All right. So what we can see here is what you see here is a live feed of the payload. So this is a web UI that is hosted from the payload itself. And this is now what I call mission control. And Cobalt 1 is the payload's code name, but I just suited it as 06BN and BACAR. But my sole core purpose of this flight was mainly software. So what I mean by software is that so the Cobalt 1's primary mission is to test a unique set of software focusing on autonomous fault detection and fault recovery that is paramount to the success of the CubeSat that I plan to launch in 2027, 2028 that I call CubeSat Alpha's survival as it lives its soul life in space. And we've mainly focused on fail-safe recovery algorithms, autonomous deployment, self-repair, diagnostics, and troubleshooting of software on board during its flight. Cobalt 1's second mission is to monitor internal environments inside payload, such as temperature distribution inside the payload, humidity fluctuations, hardware performance fluctuations. This includes power consumption, I/O2C, CPU clock, computing resources, etc., as well as hardware behavior in extreme cold. So as we can see here is our CPU during our flight. So let me tab it. So what we can see here is our duration. So what I have noticed is that the Pi did indeed crash a few times. So there is a bug with the timing. But what's actually interesting here that we can see is how warm it actually was inside. Because I actually also thank you to Keith for the polystyrene for that what also kept it warm, but I also designed mine for the heat distribution because I used PETG. And the reason why I use PETG, especially white, is to reflect the sunlight off. And that was the main idea for that, but that was the main interesting part here. And if we go over here now to our interesting part, which is our gyroscope data. Go into here. So what I did it was split what we call the raw data and the smooth data. So I created an algorithm that will do that for me, and then I used the library called matplotlib that generates the charts for me. So the interesting part over here is especially the acceleration or rotational velocity. So this, as you can see, I put into sections. So it is, now we're looking at ascent. So for linear g-force, I peaked about 1 degree and fluorescent, or rotational velocity, we're looking about max about 1 to 2 degrees per second. So this is now our raw data. So what we're going to do here is now this is where we're going to get to the fun stuff. So now this is now smooth data. So you can see how how human readable it is. So yellow is our total. Then A is our X. So I treat it as a cube. So X is our horizontal, Y is our width, and Z is our height. So as you can see here, our acceleration is starts about 1.5, and as the balloon bursts, you see how it plummets down to about -1, which I still have a bit of doubts because I definitely think it was a bug or interference that was causing. Then over here is the rotational velocity. As we look here, this is my favorite part. It's definitely the x-axis, the red one here, how it climbs to about 500 degrees a second, and it slowly steadies down. And then we look at the y-axis. And when we look at our descent, and over here, the reason why it's a bit flat is I think this is where it's starting to. There was a bug in here because the module that I actually needed was definitely the barometer. I didn't put in because of time, but over here, if we look by the descent. So over here, as we start, this is now where the balloon bursts. So what amazed me was how it was erratic and how it actually will steady it down. And yes, I will provide these charts to the public. And the interesting fact here is our impact. So the reason why it's blank is the internals actually literally tore themselves apart. Well, the wiring. So that's one of the features I want to patch for Quad 2. And also another feature as well is the simulation that I'm working on. So I know we're tight on time, and so I will cover that in my main presentation I'm gonna do in future that I'll upload to my channel once completed. And yeah, because I know this doesn't look much, but it's more to it that meets the eye. And yeah, thank you for listening, and yeah, I'm gonna bid you all a 73. And okay.
Thank you very much, Nathan. There are very interesting patterns in that data, and I saw Hendrik saying the similarities to some of his data as well. So very, very interesting. And sorry that we're running out of time, everybody, and we are not giving you sufficient airtime there, Nathan. But look forward to the presentation on your channel. So
Will do. And sorry about the mic situation.
No problems at all. These things happen. I'd like to then say once again a very, very big thank you to the Secunda Amateur Radio Club. They make these BACAR flights possible. And as Christo has mentioned, he thanked the SARL, and I know that the SARL are very, very supportive of BACAR as well. I would like to encourage everyone to give it a try. Come out to the Secunda if you can. I know that's not always viable, but you can participate in BACAR remotely by downloading the data, tracking the whisper beacons, receiving SSTV images, and supporting those who do manage to get up to BACAR. You can even courier your payload to BACAR if you like, and we can install it and put it in the train and do that on your behalf if you can't make it to Secunda. That's been done in the past as well. Then I'd like to say a very big thank you to all the payload flyers for your presentations this evening, for taking the time out to prepare for us and to do the talks for us this evening. And as I have suggested to many, please do publish your reports in Radio ZS. I think it's very interesting and will help the amateur radio community. Then finally, a big thank you to all those who joined us this evening for this Power Hour Tech Talk. And this will be the last one of the year 2025. So we bid you happy holidays and a wonderful new year. Thank you, everyone, and good night. This is HR. Relinquishing more frequencies and more general use. Ooh.
Yeah, thanks, Keith. I had to watch on the phone, unfortunately, but got it all. 7-3.
7-3,
Okay,
everyone.
thank you. Thank you, Graham. I was trying to chat to you earlier, but you weren't answering me. You were probably getting coffee or something. 73 there, Graham.
7-3,
No, all
Keith.
good. I had to switch. I was on the PC and that also wasn't working, so I had to end up switching onto the phone because the audio is not working on the PC. But yeah, got it all. Fantastic. Thanks for doing it. We chat soon. 7-3.
73, Graham.
7-3.